Problem set is due on Thursday, but at the usual time. There won't be lecture. I'm leaving for travel this afternoon. But we will have a problem session on Friday because we will use that as our opportunity to have a review session for your course. For the upcoming exam. Yeah.
And then would you have your normal office hours on
My normal office hours as well. Yep. So the exam is a week from tomorrow, in the evening, as we've had it before. It'll cover the material that's in lectures 8 through 19, as listed on the, not on a printout version, but on, what it says in the web. And the problem sets that start from the second problem on problem set 5 through problem set 9. It won't include the problem set that's due on Thursday. Okay? That's not the time to absorb all of that. RTA promised. You will have the graded homework for you, and they'll be in the front office. Okay? All the solutions are posted. So this includes the material that goes back a little bit now. So it's time to review it. That includes the discussion of fine and hyperfine structure, relativistic corrections to the hydrogen atom. Includes time-dependent perturbation theory and applications, and includes the unit we just finished on rotation, symmetry, tensors, and Fischer-Eckert theorem. Okay? A whole lot of stuff. All right, so again, it'll be similar format to the previous exam. It's a closed book, but I will give you any equations you need, and if there's something that you forgot that you think you need, you just ask me during the exam, and we'll work to make it shorter. Okay? All right. Finally, there will be one more problem set. It will be extra credit. And there will be, as last semester, an optional oral final. So that means that I will make up a temporary grade for you before the end of this before the last day of class. And you can take the grade and run, or you can roll the dice and take the final. All right? Okay. Very good. So we're now moving to the final subject that we're going to cover this semester, and that's the problem of quantum mechanics of identical particles. So, as it stands, our description of non-relativistic quantum mechanics is incomplete, because there's something that we have to impose that on the allowed quantum states of the system when we have identical particles. That does not follow from any of the postulates that we have already put in place for quantum mechanics. Okay? That is to say, in non-relativistic quantum mechanics, there is what we call super selection rule. Regarding the possible quantum states of a collection of identical particles. Now, I emphasize this word non-relativistic. I'll come back to this in a moment. So let's just hold that in abeyance and return to that question. Why am I saying in non-relativistic quantum mechanics opposed to relativistic quantum mechanics? And you know what? So of course, the existence of this superselection rule was formulated fairly early on in the development of quantum theory, before the development of quantum field theory and relativistic quantum mechanics. And of course, we have lots of evidence for this. Empirical evidence. We have the periodic table, right? And we know that the ground state of atoms in the periodic table isn't all the electrons in, say, the 1s state that we would have for hydrogen, right? So I mean, we have what we usually have the usual configurations that we see that we learned, whenever in high school, electron configurations. We have hydrogen, 1s, helium, we have 2 electrons, they're both in 1s, and then we get to lithium, and then we have that. And then we have, what's after that? Beryllium. Boron is 1s, 2s, 2p, etc., etc. Right? So this is saying that we fill up these orbitals this way. I mean, of course, this is not, we have to really get into the guts of this is more complicated in the sense, of course, that the electrons are interacting with one another. So it's not a set of non-interacting hydrogen-like orbitals that you just fill up. But this gives you some of the basic structure. The fact that that we had this structure, this led to Pauli to formulate his exclusion principle. That no 2 electrons could be in the same exact quantum state. And they could be in the same orbital, but then they would have to have opposite spins, and since the electron only has 2 spin states, you can only have sort of 2 electrons per orbital. Of course, there's other evidence that was seen before. There's the evidence related to the effect of quantum statistics on thermodynamics. So the fact that there were macroscopic properties seen in many body systems that seem to be different than assuming thermodynamically, just in terms of kind of random occupation of microstates that we know in thermodynamics, the available microstates that are available for identical particles is different than the available microstates that are available when the particles are not identical, right? And that we see, I mean, this wasn't early evidence, but we see this now. For example, we have the notion of the Fermi surface or the Fermi level. For example, if I have a solid, and this is how a field effect transistor works. That is to say, I have some tunnel barrier, and if I apply a voltage bias to it, there's a Fermi level, and I can only tunnel through if my energy is above the Fermi level, because I can't occupy, again, another level because it's already occupied. It's another example of the Fermi exclusion principle. Or we have what Einstein and Bose predicted early on in Bose-Einstein condensation. So if I have a set of a gas of identical particles that are bosons, then if I think about, there's a kind of wave packet associated with these bosons that might overlap with one another. And the extent of that wave packet in a thermal context is related to the thermal de Broglie wavelength, because that tells you something about how much coherence there is in that wave packet. So there's a thermal de Broglie wavelength. And when the distance between the particles is on the order of the thermal de Broglie wavelength, something different will happen. And that, say that distance is about, the cube root of the density. This is the number density of bosons, n, times when this is of order 1, then we expect that the identical particle nature matters. And this leads me to a critical temperature for a quantum phase transition. VEC. So this is somewhat empirical stuff, but it does impose a new rule that we have to add to our postulates of in quantum mechanics. Now we could see this, why this we kind of expect this to be true, even if we didn't have this empirical evidence, based on some of our notions of what we expect quantum mechanics to be like. Why do I mean that? Well, in quantum mechanics, in principle, indistinguishable processes interfere. Right? That was kind of our cornerstone from the very beginning of how we thought about quantum mechanics. If there are processes that happen, and there's nothing in the universe that tells me which of those processes happened, in principle, it's not stored anywhere, then I have to think about the probability amplitudes for those processes and interfere them. So here's an example of such a case. Suppose I have two identical particles, and they're going to collide with one another, scatter. Okay? So I have a collision or a scattering event. Right? Now, let's say these two particles come in, they overlap with one another, right? And then at the end of the day, somehow, through some process, they come out. So I could call these particles A and B, they come together. But at the end of the day, I don't know if this was A or B. There were two different processes that could happen. I could have the situation where the two particles come in and scatter like that. That's process one, right? Or I could have a process where they bounce off one another and go like that. Those two processes are indistinguishable. I can't tell. There's nothing that tells me which of those processes happened. So I have to think about the interference between those processes, which means there's something that quantum mechanics better deal with, the fact that these are in principle indistinguishable. Whereas classically, at every point it's on a particular trajectory. So these are distinguishable classically. Quantumly, well, once they're in here, I can't tell what's going on here, and I can't keep track of which trajectory the particle is on. All right. So, with that said, what we want to do is write down the formalism with which we need to treat these kinds of identical particles. And so there's an additional symmetry that we impose. For identical particles. Exchange symmetry. All right. So let's just start with two particles. Okay. Suppose I have two identical particles. Call them 1 and 2. Okay? They're labels of the two particles. Of course, they're identical, so those labels are going to kind of be meaningless at some point. But let's just first call one of them 1, the other one 2. I don't really know which one is which. Okay? Now, if I just said I had two particles, and each particle lived in some Hilbert space, H, then the total Hilbert space for this, we would typically write down as the tensor product of the two Hilbert spaces. The Hilbert space for particle 1 and the Hilbert space for particle 2. That's what we would do. Because for different degrees of freedom, that's our general rule in quantum mechanics. For every degree of freedom, there's a Hilbert space, and then the joint Hilbert space is the tensor product between those Hilbert spaces. Okay, so now let me define the exchange operator. P12. Okay? And P12 acts on elements of this joint Hilbert space as follows. If I have some state, if I start in a product state, on the joint Hilbert space, then I say in that, but I exchange the states. Okay? So that's the definition of this for all states, phi A, phi B, in the two Hilbert spaces. Okay? And it acts on operators such that if I have some operator that acts on particle 1 and some operator that acts on particle 2, then this is a exchange, then this is this operator acting on 1 tensor, this operator acting on 2. So it has those effects on product states and product operators, and anything else could be made of the superposition of those. Yeah. Oh, sorry. All right. So, right. So notice here the way I've defined this on this kind of space, that this guy if you do it twice, it's the identity. Okay? So that means that the eigenvalues are plus or minus 1. The eigenvalues of this exchange operator. All right. So the super selection rule says the following. For identical particles, only allowed states are eigenstates of exchange. At the moment, we're just imposing that as a rule. I'll come back to this in just a moment. So in the case of two particles, my Hilbert space here decomposes into two subspaces. One subspace associated with the symmetric under exchange, and one associated with the antisymmetric under exchange. And so I can write this as a direct sum of these two Hilbert spaces. One Hilbert space associated with the symmetric subspace, and one associated with the antisymmetric subspace. Notice, neither of these Hilbert spaces are tensor product spaces. That is to say, there are states, I can't just willy-nilly, in a tensor product space, I need to be able to take any two states in each of the subsystems, in each of the degrees of freedom, and be able to superpose them. And there are states like that that just aren't in these Hilbert spaces. So the space of symmetric under exchange and the space of anti-symmetric under exchange are not tensor product spaces of the two Hilbert spaces of particle 1 and 2. Okay? That's a confusing point, because people always get confused. We're going to come back to this about this question about entanglement and what it means to talk about entanglement for identical particles. And the bottom line is here. If we don't have a tensor product structure, it's meaningless to talk about entanglement. I'll come back to that point. Yes, Stephen?
This is basically just for bosons, but what's the rules for fermions?
No, I didn't say this is for bosons. There is a symmetric and an antisymmetric case. The symmetric ones are the bosons. And the antisymmetric ones are the fermions. So, what the superselection rules says that you can only have one or the other, right? So nature divides elementary particles in 3 space plus 1 time dimension into 2 classes. Bosons, symmetric under exchange, and fermions, antisymmetric. Now, yes, I mean,
Maybe a stupid question, but how do you know that you can divide the total Hilbert space only to symmetric and antisymmetric, and you don't have
because this because the eigenvalues of this operator span the space. Right? I mean, it's just like if I had even and odd functions, right? I can always write any function is a linear combination of an even part and an odd part. Now, I've said a couple of somewhat cryptic things here. And let me explain now what I mean by this. So, in non-relativistic quantum theory, this is just a rule. We don't really know where it comes from. It's, a Platonic form picked from the sky. God inscribed it, and it's the law. But what we do know is that actually, so before I say that, well, of course, what we know is that these 2 classes of elementary particles, these are the ones that have integer state spin. And these have half integer spin. So the elementary particles that have integer spin are bosons, and the elementary particles that have half integer spin are fermions. Again, plucked from the sky. Take a bite, it's delicious. Now, what is actually true is what is known is the spin statistics theorem. So, in relativistic, quantum theory, we have a couple of things that are true that aren't obvious from what we know about non-relativistic theory. First of all, it's necessarily many-body. We cannot have a well-defined relativistic quantum theory of one particle, or any fixed number of particles. Particles can be created and annihilated in relativistic quantum theory. We can't consistently write down a theory without that. So first of all, we're in a many-body theory. Secondly, we have another property having to do with not the Hilbert space, but space-time. And that's Lorentz invariance. So Lorentz invariance is a principle of causality. It's how we understand causality in modern physics, through the theory of special relativity, or general relativity if we were more ambitious. And what is true is that these two properties together give us these properties. It's amazing that you can prove from Lorentz invariance this connection between spin and statistics. It's necessarily the case, if you're going to have Lorentz invariance in quantum field theory, that the half-integer fields, the fields associated with half-integer spin, are fermions. They're antisymmetric under exchange. And for integer spin, they're symmetric under exchange. And that's something we won't prove here because we need to quantum field theory, but it's something to look forward to. Okay? There's another little cryptic thing I said here, which is 3 space plus 1 time. We'll come back to that. But this, I kind of put a little sleight of hand there about what was that I expected when I did an exchange twice. I came back necessarily to the same thing. And in fact, if I had a quantum field theory in 2 space plus 1 time, things can be different. We can have different kinds of statistics. We can have things that are beyond bosons and fermions. We can have anyons. Yes, Stephen?
Does a 3 space plus 1 time deal with the Lorentz invariance?
Both of those things they're both connected. So if I have Lorentz invariance in 3 space plus 1 time, then I can make this connection between integer spin and symmetric under exchange, and half integer spin and antisymmetric.
And these anyons in the 2 plus 1 space, they can have quarter spins, right?
Well, in some sense, they have anything. That's why they call it anyon. Okay. Maybe we'll come back to that in just a little bit. All right. Very good. So this follows, we have this kind of either bosons or fermions, depending on it. Now, one other thing I should say here, I talked about elementary particles. There's some notion that there's sort of fundamental particles like the electron and the muon and the W boson, what have you. But we can also have composite particles. So we could have a proton, right, which is made up of quarks. And it can have a composite spin. And that, whether it's composite spin or is integer or half integer, determines whether that particle is a boson or a fermion. Okay? Let's come back to that as well. So I can have, for example, a hydrogen atom is what? A boson or a fermion?
Yeah.
Boson.
It's a boson because it's got a proton and an electron together makes integer spin, right? So the hydrogen is a boson. For a long time, people tried to Bose condense hydrogen. It's a lot harder than Bose condensing rubidium, because it's like you can actually get rubidium colder and get to that regime where you don't need as low density. I mean, it's high density. You don't need the particles to be that close together because they can be, and if once they get too close together, well, maybe they're combined into molecules, and that's bad news if they don't Bose condense. So it's much easier to Bose condense rubidium gas, and rubidium is a boson. Well, it depends on the isotope, of course, right? Because it depends on the neutrons. So lithium-6 is a fermion, but lithium-7 is a boson. You can have different species of atoms, some of which are bosons and some of which are fermions. Yeah?
Could you ionize it and change it from boson
Sure.
to fermion?
Sure, right? I mean, it does indeed change. Of course, when it's charged, then it's different altogether. In other ways, it's very hard to Bose condense a plasma. But yeah, it makes a difference. Yeah.
So the statistics depends only on the spin, right? On the total
That's
spin,
correct.
not on the total angular momentum.
No, it depends only on the spin.
So,
Only on the spin. And again, that follows
That's
from
relevant.
statistics theorem to Lorentz variance. Yeah.
And it depends on some different, like binding or boundness or whatever, you know what I mean? I mean, the
Sure. So I'll come back to
Okay,
this
okay.
question because, of course, the constituent particles, whether we think about this as a composite or a bunch of constituent particles, I'll come back to that. It's a good question, and it's a subtle point, and it will become, I think, more apparent in a little bit. All right. So, right. So we can define symmetrization and anti-symmetrization operators. Right, so I'll define a symmetrization operator as the thing that permutes it and adds it back to itself, exchanges, and the anti-symmetrization operator. One minus that. So the projector, you could think about this as a projector onto the symmetric subspace. Let me write it that way. This is the projector onto S, and this is the projector onto the antisymmetric subspace. Right? Each of those are projectors. And so if I started with a state that was, say, particle 1 in A, this is a state that's not allowed, but I project it on the symmetric subspace, well, that's this. Then, of course, I have to renormalize it once I project it. And then similarly for the antisymmetric guy, do that. So these are allowed states. So now we're going to this gets confusing, so I want to emphasize some points here. There's two different labels here, A and B, 1 and 2. They mean different things. 1 and 2 means particle 1 and particle 2. A and B here means state A and state B. Okay? So this says particle 1 is in state A and particle 2 is in state B, or particle 1 is in state B and particle 2 is in state A. okay? And I have either the symmetric or the antisymmetric combination of those, depending on whether this is boson or fermion. Yeah.
Shouldn't the constant in front be 1 or 2 root 2? Because you had the 1/2 originally from that.
I'm saying I project it and then I renormalize it. When you project a state, it's not. So these are the allowed states. All right. So, of course, we see immediately one consequence of exchange symmetry is quantum statistics. So if I have this kind of situation where I have, think about the microstates associated with two particles, where the particles can be either in state A or state B, okay? So if these were distinguishable particles, then I could have this state, I could have this state, I could have this state, or I could have this state. Right? If they're bosons, well, I could have this state. I could have this state. But I can't have this or this state. I can only have the symmetric combination of them. And if they're fermions, what can I have?
Those two in the antisymmetric combinations.
Is this an allowed state of fermions? Is it antisymmetric under exchange? No. I can't have that state.
Must have, yeah.
There's only one state. Whereas this is a statement of the Pauli exclusion principle, that I can't have two states, two fermions in exactly the same state. That's not an allowed state because it's not antisymmetric under exchange. Okay? So what this says is that for the distinguishable cases, the probability of having two particles in the same state. For this case, what's the probability? Well, 2 out of 4, right? 1/2. In this case, 2/3, 2 out of 3. And in this case, 0. So what you see is, first of all, you have what we call Bose enhancement. That is to say, there is an enhanced probability to find two particles in the same state if they're bosons, compared to if they were distinguishable. And for fermions, well, it's completely suppressed. Yeah?
So what makes a particle distinguishable or indistinguishable is whether, let's say, I have like an electron and a muon, an electron
Yeah.
and a positron. So the only difference is, I think they were like mass and charge. Are those not considered like quantum numbers? Are they not part of the quantum state? Like, you're just not switching those quantum
Yeah,
numbers
you can
around?
think about them as quantum numbers.
Okay.
I mean, we don't know fundamentally where mass comes from, other than, you know, we've got the Higgs boson, but we don't know what those numbers are. That's one of the, you know, what the masses are kind of a mystery, one of the mysteries of the standard model. But in quantum field theory, what we just say is that there are these different fields associated with the different fundamental particles, right? They're not, I mean, in supersymmetry and things I don't know much more about, you know, we can think about them as quantum numbers, and I can change, you know, one kind of particle into another through some kind of operator. But in standard model kind of physics, we think about these sort of a priori. There's the, you know, the Dirac field of electrons and positrons. There's the, you know, electromagnetic field of photons, etc. So there's a different quantum field associated with every elementary particle in the standard model, and those are distinguishable. But otherwise, they are indistinguishable. And if I have composite stuff, well then they certainly can become distinguishable. All right. All right. So now let's talk about. Suppose I have a larger number of particles. Okay. So suppose I have n identical particles. Okay. So now there are different ways I can permute those particles, right? So there are permutations. There are n factorial configurations. All right? Of all the different permutations of the different particles. Now, the set of permutations form a group. As to say, I do two sequential permutations in a row and some other permutation, right? So that's the composition law. It's not an abelian doing them in different orders, means different permutations, right? But I can say a few things about this. So any permutation is a product of exchanges between two particles. So I can write any permutation as a series of permutations between two. This product is not unique. There are many different ways I can do that and get the same overall provision. But what is unique is the parity, let's say the number of permutations I have to do. So, not unique sequence. But the number of exchanges is unique.
Or not the number, but -1 to the number.
Right, with the parity of it, you're right. So not the number of exchanges, but the parity. Even or odd.
Just for clarification, configuration and permutation means the same thing?
What's that?
Just for clubs.
An exchange, a permutation is, I'm talking about exchange as just the particular case of the permutation between two.
Okay.
Okay, that's the language I'm using. But the parity, even or odd, number of exchanges. For each permutation. So we, as Keith correctly said, it's -1 times what I'll call sigma as a parity. Okay. So I can have an even number of exchanges or an odd number of exchanges. All right, so I can define then, so that P sub alpha be a permutation operator labeled by permutation alpha. Okay? So for example, P1, 3, 2. Right? This, what it would do, it would take a state like this and permute these guys. Right? So, I can define now a permutation, a projector onto the symmetric subspace as the sum over all permutations with a +1 sign. Okay? And the permutation on the antisymmetric case would be put a -1 if the parity is odd. Okay. So if I permute things twice, right, then that would be a +1. If I only permute it once, it's a -1, etc. Yeah?
Why does the parity, the permutation operator make it go from ABC to ACB, if you don't mind? Like,
So here what I'm saying is it permutes 3 and 2. That's what this does. So it puts the state that was associated with particle 3 now becomes the state associated with particle 2.
so it basically switches because if it was P1, 2, 3, it would be ABC still, right? It wouldn't affect anything, right?
Right, in that case,
It would,
our different permutations, of course, can end up being the identity.
so wouldn't
Right.
that make that 2, 1, not 1, 2 over there? Like,
They're equal. P12 is P21. It's just the same thing. Okay, so, right. So by this definition then, this permutation operator acting on a state that is in the symmetric subspace is +1 by the definition of this guy. And if I do it on a state that's in the antisymmetric subspace, then I get -1. Again, for bosons and fermions. Okay? So this gets very tedious And we're going to come back to this at the end of the semester, writing this out in this way and keeping track of all the permutations and putting on the right minus signs depending on how many times you commuted something, how many times, pain in the. And so there's a much better way to do this that we'll talk about next semester based on so-called second quantization. Okay, so let's hold that again in advance. But just because what the heck, let's think about, suppose we have, let's say we have three, suppose that I start with three states, three particles. Three states. So, just for fun, haha, let's write down what is the anisymmetric possible state, or anisymmetric. Possible state associated with these guys. We have to write down all the permutations, right? So I start with, let's say, A, B, C, right? Then I have, for example, let's write this out here, do the cyclic permutation, and I claim that this is this. Why is it a positive sign? It's two permutations. So the cyclic permutation is the permutation, it's the plus sign. So then I can cyclically permute again. And that's also a plus sign because that's right? And then I can take each one of these and compute them. So it's not a cyclic permutation, and that's going to be a minus one. Right? So that's going to have minus A with CB. That's one exchange. And then I have an exchange over there. A, right in that one. B, AC. And then I got this minus C, DA.
Second to last one should be, the first one should be B,
Oh wait, this guy. I commuted this. Where did I get this? A.
Closer. Closer.
No, why did I?
It's BCS.
Where is
BAC. BAC.
B,
AC.
AC,
You permitted the third one?
AC, yeah. I knew this. Thank you. See how tedious this is? Yuck. All right. Okay, so what we see, of course, here is that this state would vanish if any two of these were the same. Okay, so this would be the null vector.
It may just be a coincidence, but is there any reason why this looks like a cross product?
Sorry?
It may just be a coincidence, but is there any reason why this state looks like a cross product?
Well, no, there is a reason, and we'll say that in a moment. I mean, obviously there is the notion of, cross products are anisymmetric under exchange. So there's some similarity there. Yeah.
Yeah. Should it be 1 over square root of 2 or 1
No,
over
it's
square
1
root
over
of
the
6?
square root of 6, absolutely. Because that's 3 factorial, which is 6. Yeah, absolutely. Yeah.
So for the symmetric states, they'll always all be in phase? Will there always be a plus sign?
There'll always be a plus sign.
And then you just have this pi phase difference between some
Right.
states and
Now
others.
remember, we're going to come back to this. This represents 1, 2, 3. Okay? We have to think about what that means it's going to be very important. Come back to that. Now, to make that point that, Stephen, that you were noticing, there is a more convenient way to deal with writing down these states than writing out, asking yourselves to write out every permutation and see whether it's an even or odd number of exchanges. And that is the determinant. The determinant automatically allows us to take into account how many exchanges there are. That is the way the permutation is defined, right? So we can write down for states of n fermions, the joint state is what we call a Slater determinant. So, for example, this state is 1 over the square root of 3 factorial. The determinant of the matrix where I write down my 3 orbitals and then write down every possible permutation of this. So let me just write this down. Write it like this. So here's the way you fill out your determinant. I have my 3 possible quantum states, A, B, and C. Particle 1, particle 2, particle 3. What you see here is the determinant is you multiply every permutation of products of those matrix elements with an appropriate -1, depending on how many exchanges there were. This is known as a Slater determinant. Notice, it's automatically, because if I exchange any rows or columns, it's antisymmetric under exchange, right? And moreover, if any 2 of these guys were equal, well, it obeys the Pauli exclusion principle. This would be the null vector. What if these were bosons? Well, then, instead of the determinant, we have something called the permanent. So the permanent is the same thing as the determinant, except you don't put any of the minus signs in. You just multiply all the permutations together. Okay? That's called a permanent. All right, good. Now, here I haven't said anything at all about the nature of these states. I said there's a state of what have you, particle 1, particle 2, particle 3. These are states. But I haven't said anything about the nature of these states. As we know, when we talk about particles, they can have both orbital and spin degrees of freedom. right? So this is important because of the connection between spin and statistics, right? So, for example, when we talk about the permutation on these n particles, what we really mean is the following. I both permute the orbital degrees of freedom and I permute the spin degrees. I have to do everything. I have to permute all the quantum numbers associated with those two particles if they're identical. All right? So, let's, for example, let's suppose a two-particle state, two identical particle state, of the form psi 1, 2 is equal to phi 1, 2 orbit tensor chi, everyone loves chi, 1, 2 spin. Let's say I have a state like that. It's separable in the orbital and spin degrees of freedom. Okay? It's not necessarily separable in particle 1 and particle 2. So, can such a state be an eigenstate of exchange? Sure, let's look at exchange between 1 and 2, acting on this state. Right? That's equal to, I exchange the orbital degrees of freedom on the state phi, tensor into the exchange of the spin degrees of freedom, chi. Okay? Now, let's say that this is plus or minus 1. Okay, so I'm seeking for, suppose this is an eigenstate of exchange. It's an allowed state in the Hilbert space of the two identical particles. Well, as we see, this can be an eigenstate of exchange if each of these are eigenstates of exchange. But there are two different ways that can happen. So for bosons, I can have it such that under exchange the orbit is plus 1 and the spin is plus 1 under exchange. Or I could have it's anisymmetric with respect to the orbit at the same time that is anisymmetric with respect to spin. For fermions, the opposite is true. I can have something that is symmetric under orbit, but then it must be anisymmetric under spin. Or it could be anisymmetric under orbit, in which case it must be symmetric under spin. Okay? Now, in the theory of the structure of matter, where electrons play a tremendously important role, and beyond normal matter, then we know that we should look particular at the case of spin 1/2. So let's look at this important case. Identical electrons. They're fermions. They spin 1/2. Right? So, what are the eigenstates of exchange of just the spin degrees of freedom? Well, they could be symmetric. What are the symmetric cases? For 2 electrons. Any thoughts about that? I have 2 electrons, and I want them to be symmetric under exchange. Each electron could be spin up or spin down as a basis state. So what are the basis states for this case?
Up, up, plus down, down, then up, down, or wait, up, up, down, down, up, down, plus down.
Right. So let's write that. So this is 1. I could have up, down, but then I have to have a symmetric case. Or they could both be down. Right? And for, these are the symmetric underspin. And then we have the one antisymmetric state. Up, down, minus, down, up. Right? So these are eigenstates of spin exchange with eigenvalue +1 and eigenvalue -1. Now notice, we've seen these states before. This is the spin triplet, and this is the spin singlet. This has total spin 1, and this has total spin 0. Okay? This has nothing to do with angular momentum, in the sense that we didn't look at conservation of angular momentum or rotation symmetry. We just said, what are the states that are symmetric or antisymmetric under spin exchange? Okay? So, now the total state of the electron has to be antisymmetric, right, under exchange. As we said, I could have antisymmetric spin, well, then I must have symmetric space, or I could be symmetric spin, but then I have to be antisymmetric space, right? So the singlet part of the spin wave function is paired with the symmetric part of the space wave function, and the triplet part of the spin wave function is paired with the antisymmetric space. So I can have, for example, of allowed 2 electron states. I could have something that's symmetric in space paired with the singlet. Or I could have this with one of the triplets. So for example, is there a possibility of having both electrons in the same spatial orbital? Sure. But if they're in the same spatial orbital, then they must be a spin singlet. They must have opposite spins. That's, we wrote, high school chemistry, where we have the two electrons in helium in the ground state must be in a spin singlet. They have to have opposite spins, but not only the opposite spins, but we usually say one is up and one is down, but really one is up and one is down, we just don't know which one it is, and it's in an anisymmetric state. Okay? All right. We'll pick this up next week and talk about the implications of this for the structure of matter and talk about heating. All right. Remember, homework is due on Thursday, and we'll have a review session on Friday.